We know that the photoelectric effect is a phenomenon of the emission of electrons by a metal surface after absorbing light energy. The electrons thus emitted are called photoelectrons. The history of the photoelectric effect dates back to 1887, when this phenomenon was accidentally discovered by Heinrich Hertz. Hertz was investigating the production and reception of electromagnetic EM waves through an experimental setup. His setup consisted of a spark gap transmitter and a receiver in the form of a coil, with the spark gap placed at some distance from the transmitter. When a spark occurs in the spark gap of the transmitter, it produces electromagnetic waves, which are detected by the receiver, indicated by the sparking in its gap. To be able to see the spark better, he had placed the apparatus in a darkened box. However, to his surprise, Hertz observed that the maximum length of the spark was reduced when in the box. When he placed a glass panel between the source of the electromagnetic waves and the receiver, the glass panel absorbed ultraviolet radiation. This radiation had helped the electrons jump across the gap. Hence, the spark was longer before the glass panel was placed. This was due to the photoelectric effect. Because when light fell on the surface, some of the electrons on the surface absorbed enough energy from the incident radiation to overcome the attractive force of the positive ions of the material of the surface. An electron is able to escape from the metal surface only when its kinetic energy is sufficient to overcome the electrostatic attractive force. When the light was removed, the length of the spark decreased as there were no electrons being emitted by the surface. Moreover, he observed that there was no decrease in the length of the spark when he substituted glass with quartz, as quartz does not absorb UV radiation. This was one of the initial recorded observations of the photoelectric effect. During the period 1886 and 1902, two physicists, Wilhelm Holwachs and Philip Lenard, carried out a thorough investigation of the photoelectric effect phenomenon. Lenard conducted an experiment in which he placed two electrodes, an emitter or cathode, and a collector plate inside an evacuated glass tube. He connected the collector plate to the cathode by a wire through a sensitive ammeter to measure any current in the circuit. He then allowed ultraviolet radiation to fall on the cathode or emitter plate. As soon as the ultraviolet radiation fell on the cathode, a current flowed in the circuit, which was measured by the ammeter. He also observed that as soon as the ultraviolet radiation was stopped, the current also stopped flowing in the circuit. It was evident from the experiment that as soon as ultraviolet radiation falls on a cathode plate, it emits electrons. These electrons are attracted by the positive collector plate and start flowing towards the collector plate. As a result of the flow of electrons inside the glass tube, an electric current is observed in the external circuit. Further studies of this phenomenon were carried out by Wilhelm Holwachs through a very simple experiment. He mounted a clean, circular, negatively charged zinc plate on an insulating stand and connected it by a wire. took a gold leaf electroscope. He observed that when ultraviolet radiation was incident on the negatively charged zinc plate, it lost its charge. Also, he repeated the experiment by replacing the negatively charged zinc plate with an uncharged zinc plate. The uncharged zinc plate became positively charged when ultraviolet radiation was incident on it. Moreover, using a positively charged zinc plate in the same experimental setup further enhanced the positive charge of the already positive charged zinc plate. From the various observations of his experiment, Holwachs concluded that negatively charged particles were emitted from the zinc plate under the action of ultraviolet light. Holwachs and Leonard also observed that no electrons were emitted by the surface when the frequency of light was less than a certain minimum value. This minimum frequency of incident light below which no photoelectrons are liberated from the metal surface is known as the threshold frequency or work function. Threshold frequency depends on the nature of the metal surface. Certain metals such as zinc, cadmium, and magnesium respond only to ultraviolet light, as they have short wavelength and a high work function. Whereas some alkali metals such as lithium, sodium, potassium, calcium, and rubidium are sensitive even to visible light. Such metals which emit photoelectrons in visible light and have a very low work function are known as photosensitive substances. A solar panel can be used to produce electricity, and its working is based on the photoelectric effect. Let's learn about this through an experiment. Using the apparatus shown, let us study the experiment that explains the photoelectric effect. The apparatus consists of an evacuated glass or quartz tube T with a transparent quartz window W that permits radiation to pass through it. S is a source of monochromatic radiation. The evacuated tube consists of a photosensitive metal plate C, called the emitter plate or the cathode plate. This is similar to the functioning of the solar cells in a solar panel. The emitter plate C can be made of photosensitive metals like magnesium, zinc, and cadmium. These metals produce the photoelectric effect with ultraviolet radiation. However, if the source of light used is visible light, then the photoelectric effect is observed with metals like lithium, sodium, potassium, cesium, and rubidium. Another metal plate A, called the collector plate or the anode plate, is also sealed inside the evacuated tube. A battery B is connected to the emitter and collector plate to provide the potential difference through a commutator K, which is used to reverse the polarity of the cathode and the anode. The apparatus also consists of a rheostat RH, which can be used to adjust the potential difference applied between cathode and anode, and a microammeter A, which measures the photoelectric current in the external circuit. The emitter plate is now maintained at negative polarity and the collector at positive polarity using the commutator, so that the electrons emitted by the cathode can be collected by the collector or anode A. Monochromatic radiation from source S passes through the quartz window W and is incident on the photosensitive emitter plate C. The photosensitive emitter plate C starts emitting electrons. The potential difference between the cathode and the anode accelerates the electrons towards the collector plate, and hence this potential difference is now referred to as accelerating potential. The emitted electrons reach the collector, and when they flow in the external circuit, the resultant current, called the photoelectric current, is measured by the microammeter A. Using this experimental arrangement, let us now study the variation of photoelectric current when we vary the intensity of radiation, frequency of radiation, the applied potential difference between the plates, and the material of the emitter. Intensity of radiation is defined as the amount of energy incident on a unit area in a unit time. As you increase the intensity of light incident on the metal plate, you will notice that the resulting photoelectric current increases proportionally. This is because, as the intensity of light increases, the number of photons incident per second on the metal plate increases. This results in the number of emitted electrons increasing and hence increases the photoelectric current. Let us now study the effect of the applied potential difference on the photoelectric current. As you gradually increase the accelerating potential across the emitter and collector plates, you will notice that the current in the microammeter increases. We know that this happens due to an increase in the number of electrons that reach the collector plate per second. As the accelerating potential across the emitter and collector plates increases further, you will notice that the current in the microammeter reaches its maximum and remains constant. This maximum value of the current is called saturation current. Saturation current is a consequence of all the photoelectrons emitted by emitter plate C reaching the collector plate A. Now the polarity of the cathode and the anode are reversed. This potential builds a positive charge on the emitter plate that attracts the emitted electrons. The negative charge on the collector plate repels the emitted electrons. Hence, this potential is called retarding potential. As the retarding potential increases, you will observe a sharp decrease in the photoelectric current. This decrease in the photoelectric current is attributed to the decreasing number of electrons that reach the collector plate. As you continue to increase the retarding potential at a particular voltage minus V0 applied to the anode, you will notice that the photoelectric current becomes zero. The minimum negative potential V0 applied to the anode for which the photoelectric current becomes zero is called the stopping potential or cut-off potential. The photoelectric current becomes zero when the retarding potential is strong enough to repel the photoelectrons with the maximum kinetic energy. The maximum kinetic energy of the photoelectrons is equal to eV0. for higher intensities of radiation with the same frequency, the saturation current increases. This reinforces the fact that the number of photoelectrons emitted increases with the intensity of the incident frequency. However, the stopping potential remains the same for all intensities of incident radiation of the same frequency. This proves that for a given frequency of incident radiation, stopping potential is independent of its intensity. Let us now study the effect of frequency of radiation on photoelectric current and on stopping potential simultaneously. When radiation of increasing frequencies of the same intensity is incident on the emitter, then the number of photons incident per second is the same, and hence the number of electrons emitted per second will also be the same. Therefore, the saturation current is observed to be the same, though the stopping potentials V0 were observed to increase. As the frequency of radiation increases, V0 increases. This implies that the maximum kinetic energy of the ejected electrons also increases. According to the relation E V0 for maximum kinetic energy for photoelectrons. But the maximum kinetic energy is independent of the intensity of radiation. It is observed that for copper, ultraviolet radiation can produce the photoelectric effect, but radiation of lower frequencies like green or red does not cause photoelectric emission. This shows that for every metal surface, there exists a certain minimum frequency of radiation called the threshold frequency or cutoff frequency, μ0, lower than which photoelectric emission is not possible, regardless of how high the intensity is. Threshold frequency μ0 is the minimum frequency of the incident radiation required to just cause photoelectric emission from a metal surface. The threshold frequency is different for different materials of the emitter. This means that although the stopping potential varies in a linear fashion with the frequency of the incident radiation, for a certain minimum frequency, the stopping potential is observed to be zero. This was observed to be true with the case of different materials as emitters. For the same intensity and frequency of light capable of causing the photoelectric effect on different emitters, the photoelectric current remains the same, which proves that photoelectric current is independent of the material of the emitter. Another fact regarding the photoelectric effect is that the maximum time needed for the photosensitive plate C to emit electrons is 10⁻⁹ seconds or even less. Light is an electromagnetic wave consisting of electric and magnetic fields. With the continuous distribution of energy over the region of space it propagates. We have already learnt that the wave theory of light satisfactorily explains the phenomena of interference, diffraction, and polarization. Now let us apply the wave theory of light to the photoelectric effect. According to the wave theory, when electromagnetic waves are incident on a metal surface, the electrons of the metal surface absorb the energy continuously. Photoelectrons are ejected from the metal surface. If the amplitude of the waves incident on the metal surface increase, the energy of the waves increase, and hence the energy absorbed by the electrons increase. Therefore, as per the wave theory, we observe that the kinetic energy of the ejected photoelectrons increase with increase in the intensity of incident radiation. But photoelectric effect experiments show that as the intensity of the radiation increases, there is no increase in the maximum kinetic energy of the ejected electrons. We learnt earlier that the maximum kinetic energy, K max, for the ejected electrons is equal to EV0, where V0 is the stopping potential. This shows that the kinetic energy of the photoelectrons is not dependent on the intensity of radiation, which contradicts the wave theory. Therefore, the experiment shows that the maximum kinetic energy of the ejected electrons is independent of the intensity of the radiation. Further, according to the wave theory, irrespective of the frequency of the radiation of sufficient intensity over a period of time should be able to eject the electron from the metal surface. But photoelectric effect experiments show that for every metal surface, there exists a certain minimum frequency called the threshold frequency of radiation, nu0, required to just eject the electrons from the metal surface irrespective of the intensity of the radiation. This again contradicts the wave theory. According to wave theory, there is a time delay in the incidence of the radiation on the metal surface and the ejection of the electrons from the metal surface, whereas photoelectric effect experiments show that electron ejection is an instantaneous process when the radiation is incident on the metal. This contradicts the wave theory. From these facts, we can conclude that wave theory fails to explain the experimental results of the photoelectric effect. In 1905, Albert Einstein proposed a radically new theory of electromagnetic radiation to explain the photoelectric effect. This theory addresses the contradictions between particle nature and wave nature of light. According to this theory, electromagnetic radiation energy is built up of discrete units called quanta of energy of radiation. This is also called the photon. Each photon has energy E equal to h nu, where h is Planck's constant and nu is the frequency of the incident radiation. When photons are incident on the metal surface, the electron of the metal absorbs energy from the photon. The minimum energy required for the electron to just escape from the metal surface is called the work function phi naught. If the energy absorbed by the electron is greater than the work function of the metal phi naught, the electron is ejected with maximum kinetic energy K max equal to E minus phi naught, where E is the energy of the incident photon. Let this be equation 1. This equation is referred to as Einstein's photoelectric equation. However, the electrons which are more tightly bound emerge with kinetic energy less than K max. Since kinetic energy cannot be negative, we have E greater than phi naught for photoelectric emission. And since E is equal to h nu, we have h nu greater than phi naught, or we have nu greater than nu naught, where nu naught is the threshold frequency of the metal equal to phi naught by h. Threshold frequency, nu naught, is the minimum frequency of the incident radiation required to just cause photoelectric emission from a metal surface. Since nu naught is equal to phi naught by h, we have phi naught equal to h nu naught. Let this be equation 2. Substituting the value of phi naught from equation 2 in equation 1, we have the maximum kinetic energy of ejected electrons, K max, equal to h nu minus h nu naught, since E equal to h nu. From equation 3, we observe that the maximum kinetic energy of the ejected electrons is proportional to the frequency of the incident radiation, nu, since h nu naught is constant for a metal surface. From this, we also observe that the maximum kinetic energy of the ejected electrons is independent of the intensity of the incident radiation. As the intensity of the incident radiation increases, the number of photons incident per second on the metal increases. Thereby, the number of electrons absorbing energy from the photons increases per second, and hence the number of electrons ejected per second from the metal surface also increases, thereby causing an increase in the photoelectric current. If V0 is the stopping potential for a certain frequency, nu, of the incident radiation, the maximum kinetic energy, K max, is equal to EV0. Let this be equation 4. Substituting equation 4 in equation 3, we have EV0 is equal to h nu minus h nu naught. Let this be equation 5. We observe from equation 5 that the stopping potential V0 is dependent on the frequency nu of the incident radiation, since h nu naught is constant for a given metal surface. However, the stopping potential V0 is independent of the intensity of the incident radiation and similar to the maximum kinetic energy. On rearranging the terms in equation 5 as shown, we get equation 6 as shown. Equation 6 is similar to the equation of a straight line y is equal to mx plus c, where the slope m of the graph is equal to h by e. From equation 6, as stopping potential V0 varies in a linear fashion with the incident frequency nu, a graph drawn between the stopping potential V0 taken on the y-axis and the frequency of the incident radiation taken on the x-axis is a straight line. Millikan performed the photoelectric effect experiment for a series of metals and found that the stopping potential V0 varied in a linear fashion with frequency and from the slope of the stopping potential. V0 versus frequency, nu graph, determined the value of Planck's constant using the known value of charge on electron, which is equal to 1.6 into 10 power minus 19 coulomb. The value of Planck's constant h is equal to slope of the graph into the value of charge on E. The value of h is found to be equal to 6.626 into 10 power minus 34 joule second. The intercept on the x-axis provides the value of the threshold frequency nu0. The work function of the given metal surface phi naught is equal to h nu0 can be determined since we know the value of Planck's constant h. Irrespective of the intensity of the radiation, the photoelectric emission is an instantaneous process, as was experimentally verified. As you know, the phenomenon of photoelectric effect explains that light consists of packets of energy known as quanta, and this characteristic of light exhibits during its interaction with matter. Each such packet has energy E equal to h nu, where h is the Planck's constant and nu is the frequency of light that is being used. Einstein concluded that each packet of energy can also be associated with the definite momentum P equal to h nu by c, where h is the Planck's constant, nu is the frequency of the light used, and c is the velocity of light. Each quanta has definite energy as well as momentum, and hence each packet of energy can be treated as a particle, which is called photon. Now we can say that light possesses a particle nature as well. In 1924, A. H. Compton proved the particle nature of light with his experiment on scattering of X-rays from electrons. The phenomena of scattering of X-rays from electrons is called the Compton effect. Let's now summarize the properties of photons. In the interaction of radiation with matter, like in the case of photoelectric effect, it seems as though radiation is made up of particles called photons. Each photon has energy E equal to h nu. Since nu is equal to c by lambda, we have E equal to hc by lambda, where lambda is the wavelength of light used. And momentum P is equal to h nu divided by c. All photons travel with the same speed of 3 × 10⁸ meter per second through vacuum, irrespective of their frequencies. All photons of light of a particular frequency, nu, or wavelength lambda, have the same energy and momentum, irrespective of the intensity of radiation. An increase in intensity of radiation of a given wavelength implies an increase in the number of photons crossing per unit area per second, as long as the frequency of radiation is constant. Hence, all the photons of a given frequency still have the same energy and momentum, irrespective of the intensity. The rest mass of a photon is zero. Photons pass undeviatedly through an electric field, which can be created by the charged plates of a capacitor. Hence, we can say that photons are not affected by electric field, which means they are electrically neutral. The photons also travel undeviatedly in the region between the two magnets, and so they are not affected by magnetic fields as well. In a photon-particle collision, such as photon-electron collision, the total energy and total momentum of the system are conserved. However, the number of photons may not be conserved in such a collision. This is because the incident photons may be absorbed or new photons may be created. In the case of photoelectric effect, we have seen that the photon is completely absorbed in the process of photon-electron collision. When X-rays are scattered from electrons after the photon-electron collision, a new photon is created. The experiment conducted to study the photoelectric effect led us to conclude that radiation behaves as if it were a bunch of particles, while experiments conducted to study the phenomena of interference showed the wave nature of radiation. This particle wave nature of radiation was extended to matter by Louis Victor de Broglie. De Broglie hypothesized that moving particles of matter display wave-like properties under suitable conditions. He reasoned that nature was symmetrical and that the two basic physical entities, matter and energy, must have symmetrical character. Hence, if radiation showed particle nature, so should matter. De Broglie proposed that wavelength lambda associated with the particle is equal to h divided by p, where h is the Planck's constant and p is the momentum of the particle. But p is equal to m multiplied by v, where m is the mass of the particle and v is the velocity of the particle. This equation is called the de Broglie equation, and lambda is called the de Broglie wavelength. The dual nature of matter is evident in the de Broglie equation. The left-hand side of the equation has the attributes of a waveform, while on the right-hand side are the typical attributes of a particle. Let us calculate the de Broglie wavelength of a cricket ball of mass 0.14 kilogram moving with the velocity of 40 meters per second, and an electron of mass m and charge E accelerated through a potential V, and compare the impact of de Broglie wavelength on matter. The momentum of the ball P is equal to 0.14 kilogram multiplied by 40 meters per second. That is equal to 5.6 kilogram meter per second. The de Broglie wavelength is calculated by dividing the Planck's constant with the momentum of the ball. That is 6.634 into 10 to the power of minus 34 divided by 5.6 kilogram meter per second. The ratio equals to 1.18 into 10 to the power of minus 34 meter. The kinetic energy of an electron is equal to the work done on it by the electric field K is equal to EV. Let this be equation 1. The kinetic energy of the electron is also equal to P squared divided by 2m, where P is its momentum and m is its mass. This equation can be rewritten as P equals to square root of 2mk. Substituting the value of k from equation 1, we get P is equal to square root of 2mev. The de Broglie wavelength is now calculated by substituting the value of h and p, that is, h divided by square root of 2mev. Substituting the numerical values of Planck's constant h, which is 6.634 into 10 power minus 34 joule second, mass of the electron m, which is 9.1 into 10 power minus 31 kilogram, and charge on an electron E, which is 1.602 into 10 power minus 19. And simplifying, we arrive at the equation lambda equals to 1.227 divided by square root of V nanometers. At a potential difference of 120 volt, lambda is equal to 0.112 nanometer. For the ball, the de Broglie wavelength is beyond any measurement possible and hence can be considered as negligible. Whereas the de Broglie wavelength for the electron is of the order of the spacing between the atomic planes in crystals. This is the reason why macroscopic objects in our daily life do not show wave-like properties, whereas the de Broglie wavelength is significant and measurable in the subatomic domain. According to de Broglie's dual nature theory, every moving particle, be it an electron, proton, etc., is associated with a wave nature. Such waves are known as matter waves. So, for a particle moving in a one-dimensional space, say along the x-axis, the wave function can be represented by the sinusoidal function as shown. If the position of the particle is well defined, that is, its position can be known exactly, then its wave function is a sharply peaked function where the amplitude A is represented on the y-axis. It is important to note that the wave function has zero amplitude everywhere else, except at the location of the particle. It is also important to remember that each wave function represents a component of different momentums for the particle in the one-dimensional space considered. That is, along the x-axis. Now, if we consider a number of such wave functions, each with a different de Broglie wavelength, superposing each other, it results in a wave function as shown. It is clear that the superposed wave function does not have a well-defined peak. Rather, it represents the approximate position of the particle. Therefore, we can say that there is some uncertainty, say delta x, in the location of the particle. Thus, for a finite uncertainty in the position delta x, we see that the wave function is built up of several wavelengths spread around the central wavelength. If we now look at the superimposition of increased number of wave functions representing various components of different momentums of the particle, then the superposed wave function has a peak sharper than before. This means that the uncertainty in the position of the particle delta x has decreased compared to the previous case. Thus, as we go on increasing the number of superimposing wave functions which represent the components of different momentums of the particle, we see the single wave function obtained by their superimposition resulting in a narrow peak. Thus, the uncertainty in the position of the particle reduces. When infinite wave functions representing different components of momentums of the particle are superimposed, we get a single wave function which has very sharp peak. Thus, the uncertainty in the position of the particle is reduced to zero, and thus we can locate the position of particle with maximum possible accuracy. When the uncertainty in the position of the particle is zero, we say that we have localized the particle. But for this, we used infinite number of wave functions representing the components of different momentums of the particle. In this process, we lost all information regarding the momentum of the particle. Thus, the uncertainty delta p in the determination of the exact momentum of the particle is now infinity. From this discussion, it is clear that the exact position and momentum of a particle cannot be determined simultaneously. This is the essence of Heisenberg's uncertainty principle. Heisenberg's uncertainty principle states that it is not possible to simultaneously measure the position and the momentum of a particle exactly. If delta x and delta p represent the uncertainty in the position and momentum of a particle, then, according to the uncertainty principle, delta x, delta p is greater than or equal to h cross by 2. Since h cross is equal to h by 2 pi, we have delta x, delta p greater than or equal to h by 4 pi, where h is the Planck's constant. Let this be equation 1. Rearranging the terms in equation 1, we see that greater the value of delta x, smaller will be the value of delta p, and vice versa. If delta p is equal to 0, that is, when the uncertainty in the momentum of the particle is 0, then the uncertainty in the position of the particle becomes infinity. That is, it is impossible to exactly determine the position of the particle. This implies that we do not have any idea about the position of the particle. Similarly, if delta x is equal to 0, then delta p becomes infinity. That is, if the uncertainty in position of the particle is eliminated, we cannot determine its exact momentum. To understand the uncertainty principle better, let us consider a projectile of mass 1 gram, that is 10 power minus 3 kg, moving such that the uncertainty in its velocity, delta v, is equal to 10 to the power of minus 6 meter per second. Then the uncertainty in its momentum, delta p, will be equal to m delta v. Then, the minimum uncertainty in the position of the particle is delta x is equal to h by m delta v into 4 pi. Substituting the values of the variables involved and solving, we get delta x very negligible, and hence the uncertainty in the position of macroscopic objects around us very difficult to visualize. For the same uncertainty in the velocity, if we consider an electron, then substituting the mass of electron m, which is equal to 9.1 into 10 power minus 31 kg, we get the minimum uncertainty in the position delta x for the electron, which is very huge and far greater than the size of the atom. Thus, for subatomic particles, the uncertainty in the position is very high. Hence, we can say that the uncertainty principle has a larger importance in the context of the subatomic world. The experimental discovery of diffraction of electrons by crystals by Davison and Germer established the wave nature of electrons. Here is the similar setup to the experiment conducted by Davison and Germer. The setup is placed in an evacuated chamber. It consists of an electron gun G, a nickel target, and an electron detector that is capable of moving on a circular scale. The electron detector is connected to a sensitive galvanometer used to measure current. The electron gun G is used to produce a beam of electrons. The electron gun constitutes a tungsten filament F coated with barium oxide and can be heated with a low voltage power supply. Electrons are emitted by the filament, and these are accelerated at a desired velocity by applying a suitable voltage from a high voltage power supply. The electrons thus emitted are passed through a cylinder with a pinhole along its axis, producing a fine collimated beam. This collimated beam is directed to fall on the surface of the nickel crystal. The electrons are scattered in various directions by the atoms of the crystal. The intensity of the electron beam scattered in a given direction is measured by the electron detector or the movable collector. By moving the detector on the circular scale at different positions, the intensity of the scattered electron beam is measured for different values of angle of scattering. Theta, which is the angle between the incident and the scattered electron beams. This experiment was performed by varying the accelerating voltage from 44 volt to 68 volt. It was noticed that a strong peak appeared in the intensity I of the scattered electrons at an accelerating voltage of 54 volt and at a scattering angle theta equal to 50 degrees. The appearance of the peak in a particular direction is due to the constructive interference of electrons scattered from different layers of the regularly spaced atoms of the crystal. From electron diffraction measurements, the wavelength of matter waves was found to be 0.165 nanometers. We know that the de Broglie wavelength of an electron is denoted by lambda is equal to h by p, where h is Planck's constant and p is the momentum of the electron. If the electron is accelerated from rest through a potential difference of v volt, then, substituting the values of mass of the electron, charge on the electron, and Planck's constant, the expression for wavelength is obtained as 1.227 by square root of v nanometer. In this experiment for diffraction of electrons, the peak value of intensity was observed at 54 volt. On substituting this value in the equation and simplifying, we get the associated wavelength equal to 0.167 nanometer. This theoretical value is in agreement with the experimentally obtained value of de Broglie's wavelength for electrons. The Davison-Germer experiment thus confirms the wave nature of electrons and the validity of de Broglie relation. The de Broglie hypothesis has been the cornerstone of many advancements and applications in recent times. In 1989, the wave nature of a beam of electrons was experimentally demonstrated in a double-slit experiment, similar to that used for the wave nature of light. In 1994, interference fringes were obtained with beams of iodine molecules, which are about 1 million times more massive than electrons. The de Broglie hypothesis has been basic to the development of quantum mechanics. The de Broglie hypothesis also led to the field of electron optics. The wave properties of electrons have been utilized in the design of the electron microscope that provides higher resolution compared to normal microscopes.